There is a place in the universe where light itself cannot escape. A place where the familiar rules of space and time break down so completely that even our best mathematics struggles to describe what happens there. It is not a planet. It is not a star. It is not a cloud of gas drifting between galaxies. It is something far stranger, an object so dense, so impossibly compressed, that it punches a hole in the very fabric of the universe. We call it a black hole. The name alone carries a kind of weight. It suggests emptiness, darkness, an ending, and in many ways, that is exactly what a black hole represents, the final chapter in the life of certain stars, the point at which matter collapses beyond any known force's ability to stop it. But a black hole is not simply an absence. It is one of the most powerful, most influential, and most deeply mysterious objects that nature has ever produced. Black holes shape the galaxies they inhabit. They bend the paths of light across billions of kilometers. They distort the flow of time itself, and despite decades of extraordinary research, they continue to guard some of the deepest secrets in all of physics. To understand black holes, we must begin not with darkness, but with light. We must begin with stars. Every star you see in the night sky is a furnace. Deep within its core, atoms of hydrogen are crushed together under unimaginable pressure, fusing into helium and releasing energy in the process. This is nuclear fusion, in the same process that powers our own sun, and it is the reason stars shine. The energy produced by fusion pushes outward, creating an immense pressure that resists the inward pull of gravity. For most of a star's life, these two forces exist in a careful, delicate balance. Gravity pulls inward, fusion pushes outward, and the star holds its shape, burning steadily for millions or even billions of years. But this balance cannot last forever. Every star has a finite supply of fuel. When that fuel begins to run low, the outward pressure weakens. Gravity, which has been waiting patiently since the star's birth, begins to win. What happens next depends almost entirely on the mass of the star. A star like our Sun will eventually shed its outer layers and collapse into a small, dense object called a white dwarf, roughly the size of Earth, but containing nearly the mass of an entire star. A more massive star, perhaps 8 or 10 times the mass of the Sun, faces a far more violent fate. When its core fuel is exhausted, the star collapses inward with catastrophic speed. The outer layers rebound off the ultra-dense core and are blown outward in a supernova, one of the most energetic events in the known universe. What remains behind is a neutron star, an object so dense that a single teaspoon of its material would weigh roughly 1 billion tons on Earth. But for the most massive stars, those exceeding roughly 20 to 25 times the mass of our Sun, even the neutron star stage is not the end. In these rare and extraordinary cases, the collapsing core is so massive that no known force in physics can halt the collapse. Not the electromagnetic repulsion between atoms, not the nuclear strong force that holds atomic nuclei together, not even the neutron degeneracy pressure that supports a neutron star. Gravity overwhelms everything. The core continues to collapse, falling inward without limit, compressing matter into a smaller and smaller volume until it occupies a region of space so tiny, so incomprehensibly dense that it ceases to behave like anything we recognize in ordinary experience. This is the birth of a black hole. The moment of formation is both an ending and a beginning. It is the end of a star, the final, irreversible conclusion of a process that began millions of years earlier when a cloud of gas first started to collapse under its own weight. But it is also the beginning of something new, something that will persist for an almost inconceivable stretch of time, something that will quietly shape the space around it for trillions upon trillions of years. At the heart of every black hole lies what physicists call a singularity, a point where density appears to become infinite, and the curvature of space-time becomes so extreme that our current mathematical framework can no longer describe it. The singularity is not a place we can observe. It is not a surface we could ever touch. It is a boundary of our understanding. A point where the known laws of physics reach their limit and simply stop working. General relativity, Albert Einstein's monumental theory of gravity, predicts the singularity's existence. But general relativity itself admits that something must change at that scale, that some deeper theory, perhaps one that unifies gravity with quantum mechanics, is needed to truly explain what happens at the center of a black hole. Surrounding the singularity is the event horizon. This is not a physical barrier. There is no wall, no membrane, no visible edge. The event horizon is simply a boundary in space, the precise distance from the singularity at which the escape velocity equals the speed of light. Inside this boundary, nothing can escape. Not matter, not radiation, not light, not information, as far as we currently understand. Anything that crosses the event horizon is permanently cut off from the rest of the universe. It can send no signal outward. It can never return. From the perspective of an outside observer, an object falling toward a black hole would appear to slow down as it approached the event horizon, its light stretching into longer and longer wavelengths, growing dimmer and redder until it faded from view entirely. But from the perspective of the falling object itself, the crossing would be seamless. There would be no dramatic moment of arrival, no flash of recognition, just a quiet, invisible threshold, and then no way back. This is what makes black holes so profoundly unsettling to our intuition. They are not violent in the way we might expect. They do not reach out and grab things. They do not hunt. They simply exist, curving the space around them so severely that certain paths lead only inward. Anything that wanders too close, a stray gas cloud, a passing star, even a beam of light on an unlucky trajectory, follows that curvature inward and is lost. The idea of such an object is not new. More than 2 centuries before Einstein, an English clergyman and natural philosopher named John Michael speculated about the possibility of what he called dark stars, objects so massive that light itself could not escape their gravitational pull. Writing in 1783, Michell reasoned that if a star were large enough and dense enough, its gravity would trap its own light, rendering it invisible. A few years later, the French mathematician Pierre-Simon Laplace arrived at a similar conclusion independently. But these early ideas were based on Newtonian gravity, which treats light as a stream of tiny particles affected by gravitational force. The concept was intriguing but incomplete. It would take more than a century and a complete revolution in our understanding of gravity before the true nature of black holes began to come into focus. That revolution arrived in 1915, when Albert Einstein published his general theory of relativity. In this new framework, gravity was no longer a force pulling objects together across empty space. Instead, gravity was geometry. Mass and energy curved the fabric of space-time itself, and objects moved along the paths dictated by that curvature. The sun did not pull Earth toward it. The sun warped the space around it, and Earth followed the curved path through that warped space. It was a breathtaking reimagining of one of the most fundamental forces in nature. Within months of Einstein's publication, a German physicist and astronomer named Karl Schwarzschild found an exact solution to Einstein's field equations, a solution describing the space-time geometry around a perfectly spherical, non-rotating mass. Schwarzschild's solution revealed something remarkable. For any given mass, there existed a critical radius now, called the Schwarzschild radius, at which space-time curvature became so extreme that nothing could escape. If the entire mass of an object were compressed within this radius, the result would be a region of space from which no signal, no particle, no light could ever emerge. Schwarzschild had mathematically described what we now call a black hole, though the term itself would not be coined for another half-century. At the time, almost no one believed such objects could actually exist in nature. Einstein himself was skeptical. The idea of matter collapsing to a point of infinite density seemed physically absurd, a mathematical curiosity rather than a real possibility. Surely, physicists reasoned, some unknown force or process would intervene to prevent such a collapse. Surely nature would not allow something so extreme. But nature, as it so often does, had other plans. Tonight, we trace the full story of black holes from theoretical abstraction to observed reality. We will explore how they form, how they grow, and how they shape the universe around them. We will visit the event horizon and consider what it means for space, time, and everything that falls within. We will travel to the centers of galaxies, where supermassive black holes, millions or billions of times the mass of our sun, sit quietly at the heart of nearly every large galaxy, including our own. And we will confront the questions that remain unanswered, the mysteries that black holes still hold, even after a century of discovery. This is a story about gravity at its most extreme, about space and time pushed beyond their limits, about the boundaries of human knowledge and the quiet courage of continuing to ask questions, even when the answers seem impossibly far away. Let us begin. For decades after Schwarzschild's discovery, the idea of gravitational collapse to a point of infinite density remained precisely that, an idea. A strange and uncomfortable prediction buried inside the elegant framework of general relativity. Most physicists treated it as a mathematical artifact, an extreme solution that nature would somehow avoid. The universe, they believed, must have safeguards against such extremes. Something would intervene. Some force, some pressure, some mechanism not yet understood would prevent any real object from collapsing so completely. This assumption was not unreasonable. In daily experience, matter resists compression. Squeeze a solid object, and the atoms push back. Compress a gas, and its pressure rises. Even the densest objects known at the time, white dwarfs, the remnants of dead stars, roughly the size of Earth, but containing the mass of the Sun, maintain their structure through a quantum mechanical effect called electron degeneracy pressure. Electrons, governed by the Pauli exclusion principle, resist being forced into the same quantum state, creating an outward pressure that supports the star even after nuclear fusion has ceased. White dwarfs seemed stable. They seemed permanent. And for a while, many physicists assumed that all stellar remnants would eventually settle into this quiet, dignified retirement. But in 1930, a young Indian astrophysicist named Subramanian Chandrasekhar, just 19 years old, and traveling by steamship from India to England, worked through the mathematics of white dwarf structure using the tools of both quantum mechanics and special relativity. What he found was deeply troubling. Chandrasekhar demonstrated that electron degeneracy pressure has a limit. If a white dwarf exceeds approximately 4 times the mass of our Sun, a boundary, now called the Chandrasekhar limit, the electrons can no longer support the star. The pressure fails. The white dwarf must collapse further. Chandrasekhar's calculation implied that for sufficiently massive stellar remnants, no known force could halt the inward fall. Collapse would continue indefinitely. The reaction from the scientific community was divided. Arthur Eddington, one of the most influential astrophysicists of the era, and the man who had famously confirmed Einstein's general relativity through his 1919 solar eclipse observations, publicly dismissed Chandrasekhar's result. Eddington argued that nature simply would not permit such behavior. He found the idea aesthetically repulsive, a star collapsing without limit, matter disappearing from the observable universe. At a meeting of the Royal Astronomical Society in 1935, Eddington openly criticized the young physicist's conclusions. The moment was painful, and it cast a long shadow over the study of gravitational collapse for years to come. But mathematics does not yield to aesthetic preference. In 1939, J. Robert Oppenheimer, who would later become famous for his role in the development of the atomic bomb, co-authored a landmark paper with his student, Hartland Snyder. The paper, titled On Continued Gravitational Contraction, applied general relativity to the problem of a massive star that had exhausted its fuel. Oppenheimer and Snyder showed that if the star's core exceeded a certain mass, gravitational collapse would proceed without interruption. The matter would fall inward, crossing what they described as a critical surface, the Schwarzschild radius, beyond which no signal could escape. From the perspective of a distant observer, the collapse would appear to slow down and freeze at this boundary, the light from the star growing ever fainter and ever redder. But from the perspective of the collapsing matter itself, the fall would continue smoothly past the critical surface and inward toward the center. It was, in essence, the first rigorous theoretical prediction of what we now call a black hole forming in nature. Oppenheimer and Snyder had demonstrated that gravitational collapse was not merely a mathematical curiosity, it was a physically plausible outcome of stellar death. Yet the world was not ready to listen. The paper was published just months before the outbreak of the Second World War. Oppenheimer himself was soon absorbed into the Manhattan Project, and the broader physics community turned its attention toward nuclear physics, quantum electrodynamics, and the pressing demands of wartime research. The problem of gravitational collapse was set aside not because it had been solved, but because the world had more immediate concerns. It would take more than 2 decades for the subject to fully reawaken. In the late 1950s and early 1960s, a new generation of physicists began to revisit the mathematics of extreme gravity. John Archibald Wheeler, an American physicist with a gift for vivid language, became one of the most influential voices in this revival. Wheeler spent years studying the implications of general relativity at its most extreme, exploring what happens when matter is compressed beyond all known thresholds. He grappled with the philosophical as well as the physical implications. What does it mean for information to be permanently lost behind a one-way boundary in space? What does it mean for the fabric of space-time to curve without limit? It was Wheeler who, in 1967, gave the phenomenon its lasting name. At a conference, searching for a term more evocative than the cumbersome phrases used previously: frozen star, collapsed star, gravitationally, completely collapsed, Object Wheeler settled on 2 words that captured both the physics and the mystery in a single breath. Black hole. The term was perfect. It was immediate, intuitive, and slightly unsettling. It stuck, and it transformed the public imagination as much as the scientific conversation. Around the same time, a New Zealand mathematician named Roy Kerr solved Einstein's field equations for a rotating mass, a far more realistic scenario than Schwarzschild's non-rotating solution. Nearly all objects in the universe rotate. Stars spin, planets spin, galaxies rotate. If a massive star collapses to form a black hole, it will carry its angular momentum with it, producing a rotating black hole. Kerr's solution revealed that rotating black holes have a more complex structure than their non-rotating counterparts. Instead of a single event horizon, a Kerr black hole possesses 2 distinct horizons, and the singularity at its center is not a point but a ring. The space around a rotating black hole is dragged along with it, an effect called frame dragging, so that even objects outside the event horizon are pulled into a swirling motion. This region, known as the ergosphere, is a place where space-time itself rotates so powerfully that nothing can remain stationary. Kerr's solution was more than an academic exercise. It described what real black holes in the universe are likely to look like. And as the theoretical understanding deepened, the question shifted from whether black holes could exist to whether anyone could find one. The challenge was immediately obvious. Black holes by their very nature, emit no light. They cannot be seen directly. They do not glow. They do not reflect. They are defined precisely by the absence of any outward signal. So how could astronomers hope to detect something that is, in every observable sense, invisible? The answer lay not in seeing the black hole itself, but in observing what it does to everything around it. The first real clue came not from visible light, but from a part of the electromagnetic spectrum that human eyes cannot see. It came from X-rays. In the early 1960s, astronomers began launching instruments above Earth's atmosphere to detect X-ray radiation from space. Earth's atmosphere absorbs most X-rays before they reach the ground, which is fortunate for life on the surface, but inconvenient for anyone trying to study high-energy cosmic phenomena. To observe the X-ray sky, detectors had to be carried above the atmosphere on rockets and eventually on satellites. What these early instruments revealed was startling. The universe was full of powerful X-ray sources, objects emitting radiation at energies far beyond anything produced by ordinary stars. Some of these sources were identified as remnants of supernovae. Others were hot gas in galaxy clusters, but a few defied easy explanation. They were compact, intensely bright in X-rays, and located in places where no ordinary star should have been producing such extreme radiation. One source in particular attracted intense attention. It was catalogued as Cygnus X1, the first X-ray source discovered in the constellation Cygnus, the Swan. Detected in 1964, Cygnus X1 was exceptionally luminous in X-rays and exhibited rapid flickering, with its brightness changing on timescales of milliseconds. This flickering was significant. The speed at which an object's brightness can vary places an upper limit on its size. Because changes in brightness cannot propagate across an object faster than the speed of light, an object flickering in milliseconds must be extraordinarily small, far smaller than a normal star. Yet the energy output was enormous, rivaling or exceeding the luminosity of entire stellar systems. Astronomers soon identified a visible companion star near the X-ray source, a blue supergiant called HDE 226868. By studying the motion of this visible star, they could infer the properties of its unseen partner. The visible star was being tugged back and forth by the gravitational pull of something massive, something invisible, something that emitted no light of its own. Careful analysis of the orbital dynamics revealed that the unseen companion had a mass significantly greater than 3 solar masses, well above the theoretical maximum for a neutron star. If it was not a neutron star, and it was not a visible star, then what was it? The conclusion, reached gradually and with appropriate scientific caution, was that Cygnus X1 contained a black hole, not a theoretical black hole buried in the mathematics of general relativity, a real one. An actual object sitting in our galaxy, actively consuming matter from its companion star and releasing tremendous energy in the process. The mechanism responsible for this energy release is one of the most important concepts in black hole astrophysics: accretion. When a black hole exists near a companion star, its gravitational field can strip material from the outer layers of that star. This stolen gas does not fall directly into the black hole. Instead, because it carries angular momentum, it spirals inward, forming a swirling disk of superheated material called an accretion disk. As the gas spirals closer and closer to the event horizon, it is compressed and heated to extraordinary temperatures, millions of degrees. At these temperatures, the gas radiates intensely across the electromagnetic spectrum, particularly in X-rays. The accretion disk becomes a beacon, announcing the presence of the black hole through the very light that the black hole itself cannot emit. This is the great irony of black hole detection. Black holes themselves are invisible, but the material falling toward them can become some of the brightest objects in the universe. The boundary between visibility and invisibility, between the brilliant accretion disk and the absolute darkness of the event horizon is one of the sharpest contrasts anywhere in nature. The discovery of Cygnus X1 was not universally accepted at first. Some astronomers proposed alternative explanations. Perhaps the unseen companion was not a black hole, but an unusual neutron star, or a pair of smaller objects whose combined mass mimicked a black hole. The debate continued through the 1970s, with accumulating evidence gradually strengthening the case. By the early 1990s, improved measurements of the orbital parameters, combined with refined models of stellar evolution and neutron star physics, left little room for alternatives. Cygnus X1 became the first widely accepted observational evidence for a stellar mass black hole, a black hole formed from the death of a massive star, containing roughly 15 times the mass of our Sun, lurking some 6,000 light-years from Earth. But Cygnus X1 was only the beginning. As X-ray telescopes improved in sensitivity and resolution, astronomers found more and more systems that exhibited the telltale signatures of black hole accretion. Binary star systems across the Milky Way revealed compact objects too massive to be neutron stars, surrounded by accretion disks radiating furiously in X-rays. Each new discovery added to the growing census of stellar mass black holes. These were not exotic hypothetical objects. They were a population, a class of astronomical body as real and as numerous as any other. The X-ray binary systems also provided unexpected insights into the physics of accretion. Observers noticed that the X-ray emission from these systems was not always steady. Some sources exhibited dramatic changes in brightness, flaring unpredictably and then dimming again. Others displayed quasi-periodic oscillations, regular fluctuations in their X-ray output that corresponded to orbital periods of material in the innermost regions of the accretion disk, just outside the event horizon. By analyzing these oscillations, astronomers could estimate how close the inner edge of the disk came to the black hole, and from this, they could infer properties of the black hole itself, including its spin. Spin is a fundamental property of a black hole. According to general relativity, a black hole can be described completely by just three quantities: its mass, its electric charge, and its angular momentum. In practice, astrophysical black holes are expected to carry negligible electric charge, so mass and spin are the two defining characteristics. A non-spinning black hole is described by Schwarzschild solution. A spinning black hole is described by Kerr's solution, and the rate of spin has dramatic consequences for the space around the black hole. A rapidly spinning black hole drags space-time around with it, shrinks the radius of the innermost stable orbit, and allows material to orbit closer to the event horizon before plunging in. This means more gravitational energy can be extracted from the accreting material, producing higher luminosities and different X-ray spectra. By studying these spectral signatures, astronomers learned to measure the spin of individual black holes, turning what had once been a purely theoretical property into an observable, measurable quantity. Beyond X-ray binaries, another method of detecting black holes emerged: gravitational lensing. Einstein's general relativity predicts that any massive object curves the spacetime around it, and this curvature bends the paths of light passing nearby. If a black hole happens to lie between a distant star or galaxy and an observer on Earth, the black hole's gravity can bend and focus the light from the background source, creating a temporary brightening known as a microlensing event. Astronomers have detected several candidate events consistent with isolated black holes drifting through the galaxy, invisible except for the momentary distortion they impose on the light of more distant objects. These observations suggest that many stellar mass black holes exist in isolation, unaccompanied by companion stars, wandering silently through the Milky Way. Current estimates suggest our galaxy alone may contain tens of millions to perhaps 100 million stellar mass black holes, the quiet remnants of massive stars that lived and died over billions of years. The sheer number is difficult to absorb. Hundreds of millions of black holes scattered throughout a single galaxy, most of them invisible, most of them alone, most of them doing nothing dramatic at all, simply existing as permanent distortions in the geometry of space-time, drifting through the interstellar medium like holes in the fabric of reality. Occasionally one may encounter a cloud of gas or a passing star and briefly reveal itself through a flicker of accretion, but for the most part, they remain silent. Invisible sentinels of collapsed matter, each one carrying the compressed history of a star that once burned brightly in the sky. The accumulating observational evidence through the latter half of the 20th century transformed black holes from a controversial theoretical prediction into an established component of the astronomical landscape. They were no longer a question mark in the equations. They were real objects with measurable masses, measurable spins, and measurable effects on the surrounding universe. The universe, it turned out, was populated with them, and the story of black hole discovery was far from over. Because even as astronomers catalogued stellar mass black holes scattered through the Milky Way, evidence was mounting of something far larger, far more powerful, and far more mysterious lurking at the very centers of galaxies. The story of black holes might have remained a story about stellar remnants, compact objects scattered through the galaxy, each one the quiet grave of a massive star. Fascinating, certainly, scientifically important without question, but ultimately a local phenomenon, a chapter in the life cycle of stars. Instead, the story opened outward, far outward, to scales that dwarfed anything stellar mass black holes could represent. The first hints arrived decades before anyone fully understood what they were seeing. In the early 1940s and 1950s, radio astronomers began surveying the sky with a new generation of instruments, listening to the universe not in visible light, but in radio waves. What they found was puzzling. Some galaxies, otherwise normal-looking collections of stars, were producing extraordinary amounts of radio energy from their central regions. The radio emission was far too powerful to be explained by stars alone. Something else was happening at the cores of these galaxies, something energetic beyond easy explanation. Then came the quasars. In the early 1960s, astronomers identified a class of objects that appeared star-like in optical telescopes, faint points of light, unremarkable at first glance. But when their spectra were analyzed, the results were bewildering. The spectral lines were shifted dramatically toward the red end of the spectrum, indicating that these objects were receding from Earth at tremendous velocities. And in an expanding universe, recession velocity correlates with distance. The redshifts implied that these star-like objects were not nearby at all. They were billions of light years away, and if they were that distant, then their apparent brightness meant they were producing staggering quantities of energy, in some cases outshining entire galaxies containing hundreds of billions of stars, yet radiating all that energy from a region smaller than our solar system. The objects were called quasi-stellar radio sources, soon shortened to quasars, and for several years they defied coherent explanation. No known physical process could account for such concentrated luminosity. Nuclear fusion, the engine that powers ordinary stars, was hopelessly insufficient. Chemical energy was irrelevant at these scales. Even the complete conversion of matter to energy through Einstein's famous equation could not easily explain the sustained output of the brightest quasars without invoking implausibly large amounts of fuel. The answer, when it finally emerged, was gravitational energy, and specifically gravitational energy released by matter falling toward an extraordinarily massive black hole. In 1964, the Soviet astrophysicists Yakov Zeldovich and Igor Chovikov, and independently the Austrian-born American physicist Edwin Salpeter, proposed that the immense energy output of quasars could be explained by accretion onto supermassive black holes. Black holes containing not 10 or 20 times the mass of the Sun, but millions or even billions of solar masses. The mechanism was conceptually similar to what would later be observed in stellar mass X-ray binaries, but scaled up to almost incomprehensible proportions. Gas spiraling inward toward a supermassive black hole would form an enormous accretion disk, heated to extreme temperatures by friction and gravitational compression. As the material spiraled closer to the event horizon, it would radiate vast quantities of energy across the electromagnetic spectrum, visible light, ultraviolet, X-rays, and radio waves. The efficiency of this process was remarkable. Gravitational accretion onto a black hole can convert roughly 10% of the rest mass energy of infalling material into radiation far more efficient than nuclear fusion, which converts less than 1%. A supermassive black hole consuming even modest amounts of gas could outshine an entire galaxy. The proposal was elegant, but it required something extraordinary to be true. There had to be black holes millions or billions of times the mass of the Sun sitting at the centers of galaxies. Not in theory, in reality. Gathering evidence for this claim became one of the great observational challenges of late 20th century astronomy. The difficulty was fundamental. Even a supermassive black hole occupies a tiny volume of space compared to a galaxy. The event horizon of a black hole containing 4 million solar masses, roughly the mass of the object, suspected to lie at the center of our own Milky Way, would fit comfortably inside the orbit of Mercury. Resolving such a small region at the distance of even the nearest galactic centers required extraordinary precision. Astronomers turned to indirect evidence. If a supermassive black hole sat at the center of a galaxy, its gravitational influence would affect the motions of everything nearby. Stars close to the galactic center would orbit faster than stars farther out, their velocities revealing the mass of the unseen central object. Gas clouds near the center would show characteristic spectral signatures, broadened emission lines indicating rapid orbital motion, and in some cases, jets of material would be launched from the vicinity of the black hole, accelerated to nearly the speed of light and extending thousands or even millions of light years into intergalactic space. One by one, the observations accumulated. Galaxy after galaxy showed signs of a compact, extraordinarily massive object at its center. The Hubble Space Telescope, launched in 1990 and corrected in 1993, played a pivotal role. Its sharp vision allowed astronomers to measure the velocities of stars and gas clouds in the innermost regions of nearby galaxies with unprecedented precision. In galaxy after galaxy, the same pattern emerged, a rapid increase in orbital velocity toward the center, consistent with a concentrated mass far exceeding what could be accounted for by visible stars. The masses inferred were enormous millions to billions of times the mass of the Sun, compressed into regions smaller than a solar system. One of the most compelling early cases was the galaxy Messier 87, a giant elliptical galaxy in the Virgo cluster, roughly 55 million light-years from Earth. Hubble observations revealed a disk of hot gas swirling around the galaxy's center at velocities exceeding 500 kilometers per second. The implied central mass was approximately 5 billion solar masses. Messier 87 also displayed a spectacular jet, a narrow beam of high-energy particles extending thousands of light-years from the galactic nucleus, believed to be powered by the supermassive black hole at the galaxy's heart. But it was our own galaxy, the Milky Way, that provided the most intimate and ultimately the most convincing evidence. At the center of the Milky Way, roughly 26,000 light-years from Earth, lies a compact radio source known as Sagittarius A star. Discovered in 1974, Sagittarius A star had long been suspected of harboring a supermassive black hole, but proving it required decades of patient observation. The challenge was immense. The galactic center is obscured by thick clouds of interstellar dust that block visible light almost entirely. Only infrared and radio observations could penetrate the dust and reveal what lay within. Beginning in the early 1990s, two independent research groups embarked on one of the most remarkable observational campaigns in the history of astronomy. One team, led by Andrea Ghez at the University of California, Los Angeles, and the other, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, began tracking the motions of individual stars orbiting close to Sagittarius A star. Using adaptive optics, a technology that corrects for the blurring effects of Earth's atmosphere in real time, they were able to measure the positions of these stars with extraordinary precision year after year, building up detailed records of their orbits. The results were astonishing. The stars closest to Sagittarius, a star, were moving at tremendous speeds. One star, designated S2, completes a full orbit around the galactic center in just 16 years, a remarkably short period for a star orbiting an entire galactic nucleus. At its closest approach, S2 passes within roughly 17 light-hours of Sagittarius A star, traveling at nearly 3% of the speed of light. Its orbit, along with the orbits of dozens of other tracked stars, allowed astronomers to calculate the mass of the central object with extraordinary precision. The answer was approximately 4 million solar masses, concentrated within a volume no larger than the orbit of Uranus. No known object other than a black hole could account for this. 4 million times the mass of the Sun compressed into a space smaller than our outer solar system. The gravitational influence was unmistakable. The orbital dynamics were clean, precise, and exactly consistent with the predictions of general relativity for motion around a compact, massive object. In 2020, Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics for their discovery, recognition not only of their observational achievement, but of the fact that supermassive black holes had transitioned from theoretical possibility to observational certainty. The Milky Way's central black hole is, by supermassive standards, relatively quiet. It is not actively consuming large amounts of material. It does not power brilliant quasar-like emission. It does not launch dramatic relativistic jets. It sits at the center of our galaxy in a state of relative calm, its presence revealed only by the orbital ballet of the stars around it and the faint radio glow of Sagittarius A star. Compared to the blazing quasars of the distant universe, our galaxy's central black hole is almost sleepy. But this quietness is itself informative. It tells us that supermassive black holes are not always active. A black hole shines only when it has material to consume. When the supply of gas runs low, the accretion disk fades, the jets weaken, and the black hole settles into dormancy. Still there, still massive, still warping space-time around it, but no longer announcing its presence through brilliant radiation. Many of the supermassive black holes in the nearby universe are in this dormant state. They powered quasars billions of years ago when gas was plentiful, and galaxies were still assembling through collisions and mergers. Now they sit quietly, monuments to a more energetic past. The discovery that virtually every large galaxy harbors a supermassive black hole at its center was one of the most important findings in modern astrophysics. It transformed our understanding of galactic structure and evolution. Black holes were no longer incidental objects, rare curiosities scattered here and there. They were fundamental components of galaxies, intimately connected to the formation and growth of the very structures they inhabited. And as observations improved, a startling correlation emerged. The mass of a galaxy's central black hole was tightly related to the mass and velocity dispersion of the galaxy's central bulge of stars. Bigger bulges harbored bigger black holes. The relationship was too tight to be coincidental. It implied that the growth of the black hole and the growth of the galaxy was somehow linked, that they co-evolved, each influencing the other across billions of years of cosmic history. How this co-evolution works remains one of the most active areas of research in astrophysics. One leading idea involves feedback. The energy released by an actively accreting black hole heats and expels gas from the surrounding galaxy, regulating star formation and limiting the black hole's own growth. When the black hole consumes too much material and becomes too luminous, its radiation and jets push gas outward, cutting off the fuel supply. The black hole dims. Star formation slows. Eventually, gas cools and settles back inward, reigniting the cycle. This feedback loop may be one of the key mechanisms that determined why galaxies look the way they do, why they are not simply chaotic collections of stars, but organized structures with characteristic sizes, shapes, and populations. The universe, it seems, was shaped not only by the light of stars, but by the darkness of black holes. The most luminous objects in the cosmos and the most invisible ones are, in some profound sense, two faces of the same phenomenon. Matter and gravity, locked in a relationship that built the galaxies we see today. For all the evidence accumulated by the end of the 20th century, the X-ray binaries, the orbital tracking of stars around Sagittarius A star, the spectral signatures of accretion disks in distant galaxies, every observation of a black hole had been indirect. Astronomers had measured the effects of black holes on their surroundings. They had weighed them through the motions of companion stars. They had detected the radiation from superheated gas spiraling toward them, but no one had ever detected a signal that came from the black holes themselves, from the warping of spacetime produced by black holes in motion. That changed on September 14, 2015, and the signal that arrived was not light. It was not X-rays or radio waves or infrared radiation. It was something far more fundamental. It was a ripple in the fabric of space-time itself. The existence of such ripples, called gravitational waves, had been predicted by Albert Einstein nearly a century earlier, in 1916, just 1 year after the publication of general relativity. Einstein showed that when massive objects accelerate when they orbit each other, collide, or undergo violent asymmetric collapse, they disturb the geometry of space-time in a way that propagates outward. At the speed of light, much as a stone dropped into a pond sends ripples across the water's surface. These gravitational waves carry energy away from the source, stretching and compressing space itself as they pass through it. In principle, any accelerating mass produces gravitational waves. In practice, the effect is extraordinarily weak. The gravitational waves produced by everyday objects, a spinning top, a swinging pendulum, even a pair of orbiting planets, are so vanishingly small that they could never be detected by any conceivable instrument. To produce gravitational waves strong enough to measure, nature requires extremes. The most powerful sources are systems involving the most compact, most massive objects, moving at the highest velocities precisely. The conditions found when two black holes orbit each other and spiral inward toward collision. Einstein himself doubted that gravitational waves would ever be observed. The distortions they produce in spacetime are almost unimaginably small. A gravitational wave passing through Earth might stretch or compress the distance between 2 points by less than 1,000th. The diameter of a proton are changed so tiny that it seems to vanish into the noise of ordinary thermal vibrations, seismic tremors, and the random jostling of atoms. Measuring such a change required not only extraordinary precision, but also a fundamentally new kind of observatory, one that listened not with mirrors or antennas, but with laser beams stretched across kilometers of empty space. The instrument that ultimately achieved this measurement was the Laser Interferometer Gravitational Wave Observatory, known as LIGO. The concept behind LIGO is deceptively simple. Two laser beams are sent along perpendicular arms, each several kilometers long, and reflected back to a central detector. Under normal conditions, the beams return in perfect synchronization, their light waves cancelling each other out. But if a gravitational wave passes through the detector, it stretches one arm and compresses the other by a fractionally different amount, disrupting the synchronization and producing a tiny but measurable signal in the detector. The sensitivity required is staggering. LIGO's arms are 4 kilometers long, and the instrument must detect changes in their length smaller than 1/10,000th the diameter of a proton. The project took decades to develop. Conceived in the 1970s and 1980s by physicists Rainer Weiss, Kip Thorne, and Ronald Draver, LIGO faced enormous technical challenges, skepticism from parts of the scientific community, and the constant pressure of justifying its considerable cost. The original LIGO detectors, which began operating in 2002, were sensitive, but not sensitive enough. They ran for several years without detecting a gravitational wave. It was only after a major upgrade producing what is called advanced LIGO that the instrument achieved the sensitivity needed to detect the faint whisper of colliding black holes from deep space. On September 14, 2015, just 2 days before advanced LIGO was scheduled to begin its first official observing run, the detectors at both LIGO sites, one in Livingston, Louisiana, and the other in Hanford, Washington, recorded a signal. It arrived first at Livingston, and then 7 milliseconds later at Hanford, consistent with a gravitational wave traveling across the Earth at the speed of light. The signal lasted less than 1/5 of a second. It began as a low-frequency oscillation, gradually increasing in both frequency and amplitude, a characteristic pattern known as a chirp, before reaching a peak and then rapidly fading away. The chirp pattern was unmistakable to those who had spent years modeling it. It was the gravitational signature of two black holes spiraling toward each other, orbiting faster and faster as they lost energy through gravitational radiation, until they finally merged into a single, larger black hole. The data allowed physicists to reconstruct the event in remarkable detail. The two black holes had masses of approximately 36 and 29 times the mass of the Sun. They had been orbiting each other, gradually drawing closer over millions of years, radiating gravitational waves that carried energy away from the system and caused the orbit to shrink. In the final fraction of a second, they were orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light before merging into a single black hole with a mass of approximately 62 solar masses. A simple calculation reveals something profound. 36 plus 29 equals 65, but the final black hole had a mass of only 62 solar masses. 3 solar masses had vanished. They had not been ejected as matter. They had been converted entirely into energy, into gravitational waves, in accordance with Einstein's equation relating mass and energy. In that brief fraction of a second, the merging black holes radiated more energy than all the stars in the observable universe combined. It was, by a significant margin, the most powerful event ever detected by human instruments. The detection, designated W1591, was announced publicly on February 11, 2016, and it sent a shockwave through the scientific world. Gravitational waves had been confirmed. Black hole mergers had been observed. General relativity had passed yet another test. This time, in the most extreme conditions imaginable, the collision of two black holes at velocities approaching the speed of light in a regime where space-time curvature was at its most intense. In 2017, Rainer Weiss, Kip Thorne, and Barry Barish were awarded the Nobel Prize in Physics for the achievement, but GW1 Pheno 91 was only the first. In the years that followed, LIGO, joined by the European detector Virgo and later by the Japanese detector Kagra, detected dozens more gravitational wave events. Many were black hole mergers. Some involved black holes of surprisingly large mass, challenging existing models of stellar evolution. Others involve the merger of neutron stars, producing gravitational waves accompanied by electromagnetic radiation light, gamma rays, and the telltale signatures of heavy element production in what became known as multi-messenger astronomy. For the first time, astronomers could observe the universe not only through light, but through the vibrations of spacetime itself. Each new detection added to the growing catalogue of black hole properties: masses, spins, merger rates, distance estimates. The population of merging black holes turned out to be more diverse than many had expected. Some were relatively small, consistent with the collapse of massive stars. Others were surprisingly large, 40, 50, even 80 or more solar masses, raising questions about how such massive black holes could form through ordinary stellar evolution. Were they the products of previous mergers, black holes that had already combined and then found new partners? Were they formed in dense stellar environments like globular clusters, where close gravitational encounters could pair black holes together? Or were some of them primordial formed, not from dying stars, but from density fluctuations in the early universe, moments after the Big Bang? These questions remain active areas of investigation. Gravitational wave astronomy is still in its infancy. The current generation of detectors can observe mergers out to distances of billions of light years, but they are sensitive only to a relatively narrow range of frequencies, those produced by stellar mass black holes in the final moments before collision. The mergers of supermassive black holes, which occur when entire galaxies collide and their central black holes eventually find each other, produce gravitational waves at much lower frequencies, below the range of ground-based detectors. Detecting these signals will require a new generation of instruments, including space-based observatories like the planned Laser Interferometer Space Antenna, known as LISA, which would deploy laser interferometers across millions of kilometers of space, listening for the deep, slow, gravitational hum of the largest black holes in the universe drawing together across cosmic time. The detection of gravitational waves opened an entirely new window on the universe. For centuries, astronomy had been the science of light collecting photons from distant objects, spreading them into spectra, measuring their brightness and their colors. Gravitational wave astronomy listens to the universe in a fundamentally different way. It detects not the radiation emitted by matter, but the trembling of spacetime itself, produced by the most violent events that gravity can create. And because gravitational waves interact so weakly with matter, they travel through the universe almost undisturbed, carrying clean, undistorted information about their sources across billions of light years. In a very real sense, gravitational waves allowed humanity to hear black holes for the first time, to detect not just their influence on nearby matter, but their direct action on the geometry of the universe. The chirp of two black holes merging is not a sound in the ordinary sense. It is a pattern of space-time distortion, translated into an audible frequency range for human comprehension. But when scientists first played that translated signal through speakers, a brief rising tone that swept upward and then abruptly stopped. It carried an emotional weight that transcended the data. It was the sound of two invisible objects, each containing the compressed remains of a dead star, falling together in a final embrace and becoming one. It was the sound of space-time ringing like a struck bell, then settling into silence. It was confirmation that the universe communicates not only through light, but through gravity, and that we had finally learned to listen. Even after the detection of gravitational waves confirmed that black holes could be heard, one fundamental milestone remained. No one had ever seen one, not directly, not as an image. Every observation to date had been indirect orbital motions, X-ray emissions, spectral signatures, gravitational ripples passing through laser beams. Each method revealed the presence and properties of black holes through their effects on surrounding matter or on space-time itself. But the black hole as a visual object, the dark silhouette of the event horizon against the glow of superheated gas, had never been captured. It existed only in simulations, in artists' renderings, in the theoretical predictions of general relativity translated into computer models. The question was whether it could ever be observed for real, whether any telescope, anywhere, could achieve the resolution needed to resolve a shadow smaller than our solar system at a distance of millions or billions of light years. The difficulty was almost absurd in its scale. The supermassive black hole at the center of the Milky Way, Sagittarius, a star, despite containing 4 million solar masses, subtends an angle on the sky, roughly equivalent to viewing an orange on the surface of the Moon from Earth. The supermassive black hole in Messier 87, though far more massive at 6.5 billion solar masses, is approximately 2,000 times farther away, making its apparent size similarly tiny. To resolve features on this scale, a telescope would need extraordinary angular resolution far beyond what any single dish or mirror could achieve. The solution was not to build a bigger telescope. It was to build a telescope the size of the Earth. The technique is called very long baseline interferometry. Instead of collecting light with a single dish, astronomers link multiple radio telescopes spread across the globe, synchronizing their observations using ultra-precise atomic clocks. Each telescope records the incoming radio waves, along with exact timestamps. Later, the recorded data from all telescopes are combined using sophisticated algorithms, effectively creating a virtual telescope with a diameter equal to the maximum distance between the participating dishes. If telescopes in Hawaii, Spain, Chile, the South Pole, and Arizona all observe the same source simultaneously, the resulting virtual dish spans thousands of kilometers. The angular resolution of such an instrument is breathtaking, capable, in principle, of resolving features as small as a few tens of microarcseconds, roughly the angular size of a coin viewed from across an ocean. This was the idea behind the Event Horizon Telescope, a global network of radio observatories designed to achieve resolution sharp enough to image the immediate surroundings of a supermassive black hole. The project grew over more than a decade, drawing together hundreds of scientists from dozens of institutions across more than 20 countries. The technical challenges were immense. Each participating telescope had to be equipped with specialized receivers tuned to a wavelength of 3 millimeters of frequency chosen because it penetrates the clouds of gas and dust that obscure the galactic center, while also providing the angular resolution needed to see event horizon scale structures. The atomic clocks at each site had to be synchronized to within fractions of a nanosecond. The volume of data recorded during a single observing campaign was staggering petabytes of information stored on hard drives that had to be physically shipped to central processing facilities because no internet connection on Earth was fast enough to transfer the data electronically. The first coordinated observations took place in April 2017. Over the course of several nights, 8 radio telescopes around the world pointed at 2 targets: Sagittarius A star at the center of the Milky Way and the supermassive black hole in Messier 87, designated M87 star. The data were collected, the hard drives were shipped, and then began nearly 2 years of painstaking analysis, calibrating the signals, removing noise, reconstructing images from incomplete data, testing the results against multiple independent imaging algorithms to ensure that the final picture was not an artifact of the processing method, but a genuine representation of what the telescopes had seen. On April 10, 2019, the Event Horizon Telescope collaboration held simultaneous press conferences around the world and released the first image ever captured of a black hole's shadow. The target was M87 star, the supermassive black hole at the heart of Messier, 8755 million light-years from Earth, containing 6.5 billion times the mass of our Sun. The image was deceptively simple. A bright, slightly asymmetric ring of light surrounding a dark central region. The ring was the emission from superheated gas orbiting the black hole at velocities approaching the speed of light. Its radiation bent and focused by the extreme curvature of space-time near the event horizon. The dark center was the shadow of the black hole itself, the region from which no light could escape, rendered visible not by what it emitted, but by what it blocked. The asymmetry of the ring, brighter on one side than the other, was a consequence of relativistic effects. Gas moving toward the observer appeared brighter due to Doppler boosting, while gas moving away appeared dimmer. Even this subtle detail matched the predictions of general relativity with remarkable precision. The image was not sharp by the standards of ordinary photography. It was blurry, grainy, and low in resolution. But what it represented was extraordinary. It was direct visual evidence that the event horizon of a black hole exists, that there is a real boundary in space beyond which light cannot escape, and that this boundary casts a measurable shadow against the surrounding emission. The size and shape of the shadow agreed with the predictions of general relativity to within the measurement uncertainties. Einstein's theory, formulated more than a century earlier, without any knowledge that such observations would ever be possible, had once again passed an observational test in the most extreme gravitational environment accessible to human instruments. 3 years later, in May 2022, the Event Horizon Telescope collaboration released a second image time of Sagittarius A star, the supermassive black hole at the center of our own galaxy. Imaging Sagittarius A star presented a different set of challenges compared to M87 star. Although Sagittarius A star is much closer, roughly 26,000 light-years versus 55 million, it is also roughly 500 times less massive than M87 star's black hole. Because a less massive black hole has a smaller event horizon, gas orbits it much faster. Material in the accretion flow around Sagittarius A star completes an orbit in mere minutes, compared to days or weeks for M87 star. This meant the source was changing rapidly, even during a single night of observation, blurring the image and complicating the reconstruction process enormously. The team had to develop entirely new analytical techniques to account for this variability, averaging over thousands of possible images to extract the underlying structure. The result was again a ring of bright emission, surrounding a dark central shadow, consistent in size and shape with the predictions for a black hole of approximately 4 million solar masses. The image confirmed what decades of indirect evidence had strongly suggested, that the compact object at the center of our galaxy is indeed a supermassive black hole, and that its shadow conforms to the geometry predicted by general relativity. Together, the images of M87 star and Sagittarius A star represented a turning point. Black holes were no longer invisible. They had been photographed. The dark heart of a black hole, the event horizon, the boundary beyond which the universe becomes unknowable, had been rendered visible through human ingenuity, international collaboration, and the patient accumulation of technological capability over decades of effort. The Event Horizon Telescope continues to expand. New stations are being added to the network, increasing its resolution and sensitivity. Future observations are expected to produce sharper images, reveal the structure of the magnetic fields, threading the accretion flow, and potentially capture motion, producing the first videos of gas swirling around a black hole in real time. Polarization measurements have already revealed the structure of magnetic fields near the event horizon of M87 star, providing critical clues about how jets of material are launched from the vicinity of supermassive black holes and accelerated to nearly the speed of light. These jets, which can extend for hundreds of thousands of light years into intergalactic space, are among the most powerful sustained energy outputs in the universe, and understanding their origin requires knowing what happens in the extreme environment just outside the event horizon. There is something quietly profound about the fact that the first image of a black hole looked almost exactly as physicists had predicted it would. The bright ring, the dark shadow, the asymmetric glow, all of it matched. It was a confirmation not only of general relativity, but of the entire chain of reasoning that had led from Schwarzschild's mathematical solution in 1916, through Oppenheimer's collapse calculations, through Wheeler's naming, through decades of indirect observation, to the moment when humanity finally pointed a planet-sized telescope at the darkness and saw exactly what the equations had promised would be there. The universe, in that moment, proved itself comprehensible. The mathematics that humans had built to describe gravity equations written on paper, tested in laboratories, refined through thought. Experiments and astronomical observations turned out to describe reality with astonishing faithfulness, even in the most extreme conditions nature can produce. And yet, the images also carried a reminder of how much remains unknown. The shadow tells us where light cannot escape. It tells us the size of the event horizon. It confirms the geometry of spacetime in the strong field regime. But it tells us nothing about what lies beyond the horizon. The interior of a black hole remains as inaccessible as ever, hidden not by technological limitation, but by the fundamental structure of spacetime itself. No telescope, no matter how powerful, can peer past the event horizon. The information inside is causally disconnected from the rest of the universe. The shadow is the closest we can come. It is the edge of the knowable world. We have now seen black holes detected through X-rays, weighed through stellar orbits, heard through gravitational waves, and photographed through planet-spanning radio arrays. We know they exist. We know where many of them are. We know their masses, and in some cases, their spins. But none of these observations tell us what it would be like to approach one. None of them describe what happens to space, to time, and to matter in the immediate vicinity of a black hole, in that strange and terrible region where gravity becomes so overwhelming that the ordinary experience of the universe ceases to apply. To understand this, we must return to the physics of space-time curvature and follow it to its most extreme consequences. Imagine you are falling toward a black hole, not a supermassive giant like the one at the center of the Milky Way, but a stellar mass black hole, perhaps 10 times the mass of the Sun, with an event horizon roughly 30 kilometers across. You are approaching from a great distance, drifting inward along a trajectory that will carry you closer and closer to the horizon. At first, nothing seems unusual. Space around you appears normal. Stars shine in all directions. The black hole itself is invisible, a patch of darkness ahead, noticeable only because the stars behind it are slightly distorted, their light bent around the curved space-time. But as you draw closer, the effects of tidal gravity begin to make themselves felt. Tidal forces arise because gravity is not uniform across an extended object. The side of your body closer to the black hole is pulled more strongly than the side farther away. This difference in gravitational pull creates a stretching force along the direction toward the black hole and a compressing force perpendicular to it. Near a small stellar mass black hole, these tidal forces become extreme, well, before you reach the event horizon. Your body would be stretched lengthwise and squeezed sideways, with increasing intensity, a process physicists have informally named spaghettification. The name is almost playful, but the physics is merciless. Long before reaching the horizon of a stellar mass black hole, any ordinary object, a spacecraft, a planet, a human body, would be torn apart by the differential pull of gravity acting across its length. For a supermassive black hole, the situation is different in an important and somewhat counterintuitive way. Because the event horizon of a supermassive black hole is so much larger, for a black hole of 4 million solar masses, the horizon spans roughly 24 million kilometers. The tidal forces at the horizon are actually much gentler. The curvature of space-time is spread over a vastly larger region, so the gradient of gravity across a human-sized object at the horizon is relatively mild. A person falling into the supermassive black hole at the center of the Milky Way would cross the event horizon without being torn apart, at least not immediately. They might not even notice the crossing. There would be no wall, no barrier, no flash of light, just a quiet, invisible boundary, passed without ceremony. The violence of tidal forces would come later, as the infalling observer continued toward the singularity, and the curvature of space-time tightened inexorably. This distinction between stellar mass and supermassive black holes is important because it reveals that the event horizon is not inherently a place of destruction. It is a causal boundary, a point of no return defined by the geometry of space-time, but not necessarily a place where anything dramatic happens locally. The drama is in the consequences. Once inside, there is no trajectory, no engine, no force that can carry you back outward. Every possible path through space-time leads inward toward the singularity. The future itself, in a very precise mathematical sense, points toward the center. Escaping a black hole after crossing the event horizon would be equivalent to traveling backward in time, something that general relativity does not permit. Time itself behaves strangely near a black hole. General relativity predicts that clocks run slower in stronger gravitational fields, a phenomenon called gravitational time dilation. Near the event horizon, this effect becomes extreme. A clock hovering just outside the horizon would tick extraordinarily slowly compared to a clock far away. If you could somehow hover near the horizon and then return to a distant location, you would find that, while only a short time had passed for you, an enormous amount of time had elapsed for the rest of the universe. In principle, hovering near the event horizon for a few hours of your own experienced time could correspond to years, centuries, or even millennia passing in the outside universe, depending on how close you were to the horizon. From the perspective of a distant observer watching someone fall toward a black hole, the effect is equally strange. They would see the falling person slow down as they approach the horizon, their movements becoming more and more sluggish, their light shifting to longer and longer wavelengths. The falling person would appear to redden, dim, and freeze, never quite reaching the horizon, fading into an infinitely redshifted ghost at the boundary of the black hole. From the outside, it would look as though the person was suspended forever at the edge of the event horizon, gradually vanishing from view. But from the perspective of the person falling in, none of this freezing would occur. They would cross the horizon smoothly and continue falling inward. The two experiences inside and outside are fundamentally different, and both are equally real. This is one of the deepest and most disorienting aspects of black hole physics. There is no single, universal description of what happens. The experience depends entirely on the observer's location and motion. General relativity does not provide a single objective timeline for all observers. It provides a geometry of space-time, and each observer traces their own path through that geometry, experiencing their own version of time. Inside the event horizon, the situation becomes even more difficult to describe using everyday language. The roles of space and time, in a certain mathematical sense, become interchanged. Outside the horizon, you can choose to move in any spatial direction, forward, backward, left, right, but you are always carried forward in time. Inside the horizon, the singularity lies not in a spatial direction, but in your future. You cannot avoid it, just as you cannot avoid tomorrow. Moving in any direction still carries you toward the singularity, because the singularity is not a place in space. It is a moment in time, the final moment for anything that crosses the horizon. What happens at the singularity itself remains one of the deepest unsolved problems in all of physics. General relativity predicts that the curvature of space-time becomes infinite at the singularity, that matter is compressed to infinite density in zero volume. But most physicists believe that this prediction signals a breakdown of the theory rather than a literal physical reality. Infinities in physics are almost always a sign that the mathematical framework being used has reached the limit of its applicability. The singularity is not so much a prediction of what actually happens as an admission that general relativity cannot describe what happens in this regime. Something else must take over. Some deeper theory, one that successfully combines gravity with quantum mechanics, is needed to describe the physics at the center of a black hole. This brings us to one of the most celebrated and still unresolved puzzles in theoretical physics, the black hole information paradox. In 1974, the British physicist Stephen Hawking made a theoretical discovery that stunned the physics community. Working at the intersection of quantum mechanics and general relativity, Hawking showed that black holes are not perfectly black. They radiate very faintly, very slowly, but they radiate. The mechanism is rooted in quantum field theory, the framework that describes how particles and fields behave at the smallest scales. In the vacuum of empty space, quantum mechanics predicts that pairs of virtual particles are constantly being created and annihilated, flickering in and out of existence so briefly that they normally leave no lasting trace. But near the event horizon of a black hole, something unusual can happen. One member of a virtual pair may fall into the black hole, while the other escapes to infinity. The escaping particle carries positive energy away from the black hole, and the infalling partner effectively carries negative energy inward, reducing the black hole's mass. Over time, this process causes the black hole to lose mass and shrink. The emitted radiation, now called Hawking radiation, has a thermal spectrum, meaning it resembles the glow of a warm object with a temperature inversely proportional to the black hole's mass. For astrophysical black holes, those with masses of several solar masses or more, the temperature of Hawking radiation is extraordinarily low, far below the temperature of the cosmic microwave background. In practice, these black holes absorb more energy from the universe than they emit, and they grow rather than shrink. Hawking radiation is utterly negligible for any black hole that currently exists. But the theoretical implication is profound. Given enough time, an almost unimaginably long stretch of time, far exceeding the current age of the universe, every black hole will eventually evaporate completely, losing all its mass through Hawking radiation and disappearing. The paradox arises from the nature of the radiation itself. Hawking's original calculation indicated that the emitted radiation is perfectly thermal random, featureless, carrying no information about what fell into the black hole. If this is correct, then when a black hole evaporates completely, all the information about everything that ever crossed its event horizon, every book, every star, every quantum state would be permanently destroyed. But this violates a fundamental principle of quantum mechanics called unitarity. which requires that information is always preserved. Quantum mechanics insists that the complete quantum state of a system at any time can, in principle, be used to reconstruct the state at any other time. Destroying information violates this principle at the deepest level. The conflict between Hawking's result and quantum mechanical unitarity has driven decades of intense theoretical research. Hawking himself initially argued that information was truly lost, that black holes represented a fundamental exception to the rules of quantum mechanics. Most other physicists resisted this conclusion, arguing that information must somehow be preserved, even if the mechanism was not yet understood. Over the years, a growing consensus has formed that information is indeed preserved, that Hawking radiation is not truly random, but carries subtle correlations, encoding the information about the black hole's contents. But exactly how this works remains one of the great open questions in theoretical physics. Proposals have ranged from modifications to the structure of the event horizon, to holographic encodings of information on the boundary of spacetime, to radical revisions of what we mean by the interior of a black hole. The information paradox is not merely a technical puzzle. It sits at the intersection of the two greatest theories in physics: general relativity and quantum mechanics, and exposes a deep tension between them. Resolving the paradox may require a theory of quantum gravity, a framework that unifies the physics of the very large with the physics of the very small. Such a theory remains elusive, despite decades of effort. String theory, loop quantum gravity, and other approaches have each offered partial insights, but none has yet provided a complete, experimentally verified resolution. The interior of a black hole and the fate of information within it remains one of the last great frontiers of fundamental physics, a place where our most successful theories reach their limits and something genuinely new is needed. The story of black holes, as we have traced it so far, falls into two broad categories: stellar mass black holes, born from the deaths of massive stars, containing roughly 5 to perhaps 100 times the mass of the Sun, and supermassive black holes, containing millions to billions of solar masses, anchored at the centers of galaxies. These two populations are well established. They have been observed, weighed, and studied through multiple independent methods. Their existence is no longer in question. But between these two categories lies a gap, a vast, unexplained desert in mass where very few confirmed black holes have been found. This is the domain of intermediate mass black holes, objects containing roughly 100 to 100,000 solar masses. They are too large to have formed from a single collapsing star through ordinary stellar evolution. They are too small to be the supermassive engines at the hearts of galaxies, and their scarcity in observational data is one of the most puzzling aspects of modern black hole astrophysics. The question is not whether intermediate mass black holes can exist. General relativity places no restriction on the mass of a black hole. Any amount of mass compressed within its Schwarzschild radius will form one. The question is whether nature actually produces them, and if so, how. Several formation pathways have been proposed. One possibility is runaway stellar mergers in dense star clusters. In the cores of globular clusters, ancient, tightly packed collections of hundreds of thousands of stars. Gravitational interactions can cause massive stars to collide and merge repeatedly, building up ever larger objects that eventually collapse into black holes significantly more massive than any single star could produce. Another possibility involves the hierarchical merging of smaller black holes. If stellar mass black holes in dense environments find partners and merge, and the resulting larger black hole then finds another partner and merges again, the mass could gradually accumulate into the intermediate range over many successive generations. There have been tantalizing hints. In 2020, the LIGO and Virgo gravitational wave detectors recorded an event designated GW190521, produced by the merger of two black holes, with masses of approximately 85 and 66 solar masses. The resulting black hole had a mass of roughly 142 solar masses, placing it firmly in the intermediate mass range. It was the first strong gravitational wave evidence for an intermediate mass black hole, and it raised as many questions as it answered. The component masses themselves were surprising. A black hole of 85 solar masses is difficult to explain through ordinary stellar collapse because theoretical models predict a gap in black hole masses between roughly 65 and 120. Solar masses arranged where the physics of stellar interiors should cause the star to be completely disrupted in a pair instability supernova, leaving no remnant at all. The existence of an 85 solar mass black hole suggests either that our understanding of massive stellar evolution is incomplete, or that this black hole was itself the product of a previous merger. X-ray observations have also produced candidates. Several ultraluminous X-ray sources in nearby galaxies emit radiation at levels that seem to exceed what a stellar mass black hole could produce through ordinary accretion, yet they are not located at galactic centers where supermassive black holes reside. Some of these sources may harbor intermediate mass, black holes accreting material from companion stars or surrounding gas, but confirming their nature has proven difficult. The mass estimates depend on assumptions about the geometry and efficiency of the accretion process and alternative explanations, including unusually oriented or super. Eddington accreting stellar mass black holes cannot always be ruled out. The search for intermediate mass black holes matters far beyond filling a gap in a classification scheme. If they exist in significant numbers, they may represent the seeds from which supermassive black holes grew. One of the deepest unsolved problems in astrophysics is how supermassive black holes became so massive so quickly. Observations of quasars at very high redshift, corresponding to times less than 1 billion years after the Big Bang, reveal supermassive black holes already containing billions of solar masses. Growing a black hole to such enormous size in such a short time is extremely difficult if you start with a stellar mass seed of only a few tens of solar masses. The accretion rate would need to be sustained near or above theoretical maximum limits for hundreds of millions of years without interruption, a scenario that many astrophysicists find implausible. Intermediate mass black holes offer a potential shortcut. If massive seeds of hundreds or thousands of solar masses could form early in cosmic history, the growth problem becomes significantly more manageable. The larger the initial seed, the faster accretion can build it toward supermassive scales. This possibility has driven intense interest in the formation mechanisms of early black holes. One hypothesis involves the direct collapse of massive primordial clouds in the early universe. Under certain conditions, particularly in regions where the gas remained free of heavy elements and molecular hydrogen cooling was suppressed, enormous clouds of gas may have collapsed directly into black holes of tens of thousands of solar masses without ever forming stars. These direct collapse black holes would have provided ready-made intermediate mass seeds that could then grow through accretion and mergers into the supermassive black holes observed in early quasars. Another possibility reaches even further back in time. Primordial black holes. Black holes formed not from stellar collapse, but from density fluctuations in the earliest moments of the universe have been discussed theoretically for decades. In the first fractions of a second after the Big Bang, the universe was extraordinarily hot and dense, and any region where the local density exceeded a critical threshold could have collapsed directly into a black hole. Unlike stellar black holes, which are limited to masses above a few solar masses, primordial black holes could in principle span an enormous range of masses, from far less than a solar mass to thousands or millions of solar masses, depending on the size and timing of the density fluctuation that produced them. The existence of primordial black holes remains unconfirmed. Observational constraints have ruled out significant populations in certain mass ranges, but windows remain open, particularly for primordial black holes in the range of roughly 10 to 100 solar masses. Intriguingly, this is precisely the mass range where LIGO has detected merging black holes. Some researchers have proposed that a fraction of the merging black holes detected through gravitational waves might be primordial in origin relics from the first second of cosmic existence rather than remnants of stellar death. If confirmed, this would be a discovery of extraordinary importance, connecting the physics of the very early universe to the gravitational wave detectable today. The question of where the first black holes came from connects to an even larger puzzle: the role of black holes in shaping cosmic structure. We have already seen that supermassive black holes co-evolve with their host galaxies, regulating star formation through feedback mechanisms. But the relationship may be even more fundamental. Some theoretical models suggest that early black holes, whether formed from massive primordial stars, direct gas collapse, or primordial density fluctuations, may have played an active role in the formation of the first galaxies themselves. By accreting gas and emitting intense radiation, these early black holes could have heated and ionized their surroundings, influencing how gas collected into the structures that eventually became galaxies. In this picture, black holes are not merely passengers within galaxies. They are architects helping to build the cosmic structures they would eventually inhabit. The fate of black holes on the longest timescales returns us to Hawking radiation. As we discussed, every black hole slowly loses mass through the quantum process that Hawking described. For astrophysical black holes in the current era, this loss is negligible, overwhelmed by the energy absorbed from the cosmic microwave background and from any accreting material. But the universe will not always be as it is now. As the cosmos continues to expand, driven by dark energy, galaxies will drift apart, stars will exhaust their fuel, and the background temperature of the universe will drop ever closer to absolute zero. In this far future, unimaginably distant from the present, black holes will become the dominant remaining objects, sitting alone in an ever-emptying cosmos, and even they will not last forever. As the cosmic background temperature drops below the Hawking temperature of a black hole, the black hole begins to lose mass faster than it gains it. Slowly, imperceptibly, it shrinks. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate a number so large that writing it out would require 67 zeros. A supermassive black hole at the center of a former galaxy would take perhaps 10 to the power of 100 years, a Google years, to vanish completely. These timescales dwarf the current age of the universe so completely that they belong more to mathematics than to human experience. But they are finite, and when the last black hole finally evaporates, releasing its remaining mass energy as a final whisper of Hawking radiation, the universe will have lost the last structured objects it contained. What remains will be a thin, cooling mist of photons and elementary particles drifting through an expanding void, a state physicists sometimes call the heat death of the universe. There is something both sobering and strangely beautiful in this picture. Black holes, the most enduring objects in the cosmos, the most resilient structures that gravity can build, will ultimately dissolve, not through collision, not through some cataclysmic event, but through the quiet, patient action of quantum mechanics, the same framework that governs the behavior of the smallest particles in existence. The largest and the smallest meet at the event horizon, and in the fullness of time, the smallest wins. We have traveled a long way together, from the death of massive stars to the birth of objects so dense that light itself cannot escape. From the first tentative calculations of a young physicist on a steamship to the global network of telescopes that captured a shadow 55 million light-years away. From the quiet mathematics of Karl Schwarzschild to the chirp of two colliding black holes ringing through the fabric of space-time. Along the way, we have encountered some of the most brilliant minds in the history of science, some of the most powerful instruments ever built, and some of the deepest questions that human beings have ever asked about the nature of reality. And yet, after all of this, after a century of theory, observation, detection, and imaging, black holes remain, in many ways, as mysterious as they were when they first appeared in the equations. We know they exist. We know where they are. We know their masses, their spins, their influence on the galaxies they inhabit. We have heard them collide. We have seen their shadows. But the deepest questions remain unanswered. What happens at the singularity? What becomes of information that crosses the event horizon? How did the first supermassive black holes grow so large so quickly in the young universe? Is there a theory of quantum gravity waiting to be discovered that will finally explain what general relativity cannot? These are not minor footnotes. They are among the most profound open problems in all of physics, and black holes sit squarely at the center of each one. There is something remarkable about an object that has been studied so intensely for so long, and yet continues to resist full understanding. Black holes are not merely difficult, they are foundational. They sit at the intersection of gravity and quantum mechanics, the two pillars of modern physics that have so far refused to be unified into a single coherent framework. General relativity describes gravity beautifully at large scales. Quantum mechanics describes the behavior of matter and energy beautifully at small scales. Both theories have been tested to extraordinary precision. Both are among the most successful scientific theories ever constructed. And yet, when applied simultaneously to the same situation as they must be at the singularity of a black hole, or during the final stages of black hole evaporation, they produce contradictions. The singularity is general relativity's confession that it has reached its limit. The information paradox is quantum mechanics' refusal to accept that limit quietly. The resolution, whatever it turns out to be, will almost certainly require a new understanding of space-time itself, a deeper theory that contains both general relativity and quantum mechanics as special cases, much as general relativity contains Newtonian gravity as a special case for weak gravitational fields and low velocities. Finding that theory is one of the great ambitions of 21st century physics. And black holes, precisely because they push both existing theories to their breaking points, are likely to be the key. They are natural laboratories for the most extreme physics the universe can produce. Every new observation, every gravitational wave detection, every sharper image from the Event Horizon telescope, every measurement of a black hole's spin or mass or accretion rate provides another constraint, another clue, another piece of the puzzle. The answers may not come quickly. They may not come in our lifetimes. But the questions are being asked with increasing precision, and the tools available to explore them are improving with every passing year. It is worth pausing to consider what it means that human beings, small, fragile, short-lived creatures on a rocky planet orbiting an ordinary star in the suburbs of an ordinary galaxy, have managed to detect, measure, and photograph objects that nature designed to be invisible. Black holes emit no light. They occupy volumes of space smaller than a city, smaller than a room, smaller, in theory, than a single point. They are separated from us by thousands or millions or billions of light years, and yet we found them, we weighed them. We listened to them collide. We watched their shadows against the glow of superheated gas, swirling at the edge of oblivion. We did this not through any single act of genius, but through the slow, patient, accumulation of understanding across generations, each generation building on the work of the last, each new instrument extending human perception a little further into the darkness. This is perhaps the deepest lesson that black holes have to teach us. Not about gravity, not about space-time, not about the fate of stars or the architecture of galaxies, but about the nature of scientific inquiry itself. Black holes were predicted before they were observed. They were named before they were found. They were photographed. A century after the mathematics that described them was written, the arc of discovery is long, and it bends not towards certainty but toward deeper and more honest questions. Every answer reveals new mysteries. Every observation opens new avenues of inquiry. The universe does not yield its secrets all at once. It offers them gradually, rewarding patience, precision, and the willingness to follow the evidence wherever it leads, even into darkness. And so we arrive at the end of our journey, not with a conclusion, but with an open horizon. Black holes are still out there, hundreds of millions in our galaxy alone, billions more scattered across the observable universe. Some are ancient, formed in the earliest epochs of cosmic history, carrying within them the compressed remnants of the first generation of stars. Some are young, born from supernovae that may have been visible to astronomers on Earth within the last few centuries. Some are growing, actively consuming gas and dust and starlight, their accretion disks blazing across the electromagnetic spectrum. Others are dormant, sitting quietly in the darkness between stars, warping the space around them without fanfare, waiting for nothing in particular. They will outlast the stars, long after the last star in the universe has exhausted its fuel and faded into cold darkness. Black holes will remain the most enduring structures in existence, persisting for timescales that dwarf the current age of the cosmos by factors beyond ordinary comprehension. And even they, in the fullness of time, will fade. Slowly, imperceptibly, particle by particle, they will return their mass to the universe through the quiet quantum whisper of Hawking radiation, shrinking across eons until nothing remains but a faint glow of thermal photons, dispersing into the expanding void. But that ending is so distant as to be almost meaningless to us. What matters now, what has always mattered, is the act of looking, the act of asking, the act of pointing our instruments at the darkest places in the universe and refusing to look away. Black holes do not care that we study them. They are indifferent to our theories, our telescopes, our hopes and confusions. They simply exist, doing what gravity has always done, curving space-time, gathering matter, shaping the cosmos. The meaning we find in them is our own. The questions we ask are our own. And the quiet courage to keep asking, even when the answers lie beyond the event horizon of our current understanding, is perhaps the most human thing of all. Tonight, as you rest, carry with you the knowledge that the universe is stranger, deeper, and more beautiful than any single mind can fully grasp. Somewhere out there, in the darkness between the stars, space-time curves inward and does not let go. Somewhere, light falls toward a boundary it will never cross back from. Somewhere, time slows to a crawl and space bends beyond recognition. These things are real. They are happening right now, as they have been happening for billions of years, as they will continue to happen, long after every question we have asked has been answered or forgotten. The universe holds its mysteries gently, and so, gently, we hold our questions. And in that holding patient, curious, unafraid, we find something that looks very much like wonder. Sleep well.